Welcome to the Enerpac Academy Bridge Launching Introduction. This training represents some of the basic knowledge which you need when discussing about bridge construction with customers. Enerpac specialists in bridge launching Jesus Gonzalez and Jeremy Stubbs provided invaluable input for this training. Let us watch an animation of how a bridge could be launched. Please note for yourself where you see evidence or perhaps possibilities for high pressure hydraulics being used in this construction. A large part of the applications in the construction and infrastructure market deals with construction of bridges. Apart from building the bridge itself, there is a variety of positioning and maintenance applications for bridges. For an overview, for better understanding and basic knowledge of bridge building, we've listed here some of the controlled hydraulic solutions which can be used, such as for lifting, lowering, pushing, pulling and hoisting. In this training we will focus on bridge launching and lifting applications. Important to know is that Enerpac is not responsible for the actual bridge launching procedures. We need to inform the customers that Enerpac does not operate the hydraulic systems. We do offer training on request to make the customers operators familiar with our hydraulic systems. As you know, Enerpac offers a complete range of controlled hydraulic solutions for all stages of the bridge building process. From the widely known classic ZE class pumps with BRD, CLRG and CLL cylinders for the bridge launching nose recovery to the newly introduced autonomous sink hoist, split flow pumps, EVO and NL launcher, there is an Enerpac solution to any bridge construction project element. But let us first work on getting to know the elements of bridge launching. In this training we will, to a certain extent, cover the following elements: the bridge construction project file, which bridge construction materials are typically used, different types of bridges, what shapes and slopes of the bridge we need to consider, the movement of the bridge and its elements or bridge displacements, what are the bridge construction parameters to take into consideration, what are the Enerpac bridge construction solutions, and finally a bit of miscellaneous information. An important part of the construction process is the bridge construction project file. Here the design engineers will register how the bridge is going to be built. The project file will also contain the technical drawings of the bridge, and it will contain information about the predicted movements of the different bridge elements. The information in the bridge construction file is crucial, as it provides you with information which is needed to provide your customer with a relevant proposal as to which controlled hydraulic systems he requires to carry out the construction. As a rule, 4 types of materials are used in bridge construction: steel, concrete, a combination of steel and concrete, and wood. Looking closer at the types of bridges which we come across, we can distinguish moving bridges, portable bridges, and fixed bridges. The pictures you see are just a sample of the wonderful bridge designs that you will find while surfing on the internet. Moving bridges are often used when maritime traffic is involved. Some examples are the swing or drawbridge, turnable bridges, and row-row or roll-on, roll-off bridges to move wheeled equipment such as cars and trucks on and off the different vessels. The military often use portable bridges for obvious reasons and purposes. We can distinguish assault bridges, special vehicle-launched bridges, the Bailey Bridge, built up from small segments for which no machines or special tools are necessary, and various types of pontoon bridges. Fixed bridges come in many different shapes. The basic building principles are beam bridge design, arch bridge design, cable stayed bridge design, and suspension bridge design. The architect's choice when designing a fixed bridge is dictated by the span the bridge has to cross. The beam design will span around 250 feet or 76 meters before needing another support. The arch bridge design tops that with a maximum span of 1,800 feet or 550 meters. The cable-stayed bridge design will span 3,600 feet or 1,100 meters without support. And the suspension bridge is the champion, with possibilities to span an amazing gap of 6,500 feet or 1,900 meters. When studying the design of a bridge and the application of controlled high-pressure hydraulic solutions, we need to have a close look at the shape of the bridge and the slope under which it is planned to be built. Different shapes may call for controlled hydraulic guidance systems. Uphill or downhill slopes may require braking systems. A combination of shapes and slopes may require both guidance and braking systems. Another important element to look for when studying the bridge construction file is the displacement of the different building blocks of the bridge. These different movements call for different controlled hydraulic solutions. We look at launching or pushing, shifting, lifting and lowering, and rotation. Let us take a look at the elements which we need to analyze when considering which controlled hydraulic solutions to advise. There's the length of the bridge, the shape of the bridge. Is it straight? Does the design follow a radius? Or is there a combination of radii with lateral angle? The slope, uphill or downhill, the building material of the bridge, and the weight per meter of bridge. Important to know is that when the weight is more than 28 metric tons per meter, always contact the Enerpac ESPA organization for correct solution considerations. And then of course there is the bridge span, the distance, indicated with D, between the pillars or piers, and the height, indicated with H, of the bridge deck. Adding to the basic bridge design elements just mentioned, please have a look at this example of an uphill launch. We need to check the weight and the angle of slope, or beta, and the perpendicular component to calculate the friction force. With that, we can calculate the pushing force needed to launch or push the bridge element. Now let's have a look at downhill launching. In this case, like before, we need to check the weight and the angle of slope, the beta, and the perpendicular component to calculate the friction force. With that, we can calculate the pushing force needed to launch or push the bridge element, but now we need to take into consideration the retention force to make sure the bridge does not slide off the slope. Now, let us look in more detail to bridge construction solutions and the Enerpac solutions applied in these constructions. Cranes are used throughout the construction world for a wide range of purposes and applications. Looking at bridges, we see that around 70% of the bridges are built using cranes. For moving and positioning bridge elements, as well as beams, decks, prefabricated parts and equipment, there's no building site without some form of crane deployment. The Enerpac sink hoist system and also the autonomous sink hoist system are perfect solutions to add to the safe and controlled movement of bridge construction elements. Traditional high-pressure cylinders and pumps are used in launching girders, which are used for moving bridge segments, in leveling of the segments, and in what we call nose recovery. And no, this has nothing to do with plastic surgery. Low-pressure hydraulics are used in bridge construction where a traveling framework is used. This type of scaffolding and temporary construction work, or false work, is used to support the formwork or mold to shape the concrete and is widely used in Asia. In some of the bridge construction projects, incremental launching is used. The bridge construction takes place next to the actual location of the bridge, and the construction is then moved step by step to the desired position. High-pressure hydraulic cylinders can be used to push or pull the construction. Two important elements must be taken into consideration: the friction coefficient μ, as seen before, for both uphill and downhill movements, and secondly, the slope, especially when the slope is more than 5 degrees. It is safe to say that with incremental launching, traditional hydraulic systems will not work. The good news is that Enerpac is a specialist in controlled high-pressure hydraulics, especially designed for incremental launching in bridge construction, as we will make clear in the following pages. When talking about incremental bridge launching, we will discuss three different systems. The spindle bar system, unique for Enerpac, which is used for pushing, retaining and as parking brake. The strand jack system as a constant tensioning system for pulling, retaining and as parking brake. And incremental launching systems for lifting combined with push and pull and also as a retaining system. Pushing and pulling can be done with two different systems: the spindle bar system and the strand jack system. The spindle bar system consists of a group of inline placed hollow plunger cylinders. Steel bars can be inserted through the cylinders, and thus the system can be used to push for load transfer and retaining the bridge construction. Looking more closely at the movements which are necessary, you need to count with one or more hollow cylinders dedicated for pushing, one or more hollow cylinders dedicated for load transfer, and one or more hollow cylinders dedicated for retaining. The cylinders for load transfer and retaining can also be used as parking brake. In the graph, you see that the diameter of the spindle bar is related to the capacity it is required to handle. This then dictates the required center diameter of your hollow cylinder. The spindle bars are manufactured in standard lengths of 6 meters. For the connection of these steel bars, special connecting nuts are used. Here are some images of actual bridge construction projects where the spindle bar system was deployed. Next is a closer look of how a strand jack system can be used in the bridge construction movement. A strand jack is a hydraulic application which may function as a linear winch as opposed to a rotary winch. A bundle of steel cables or strands are guided through a hydraulic cylinder. Above and below the cylinders are anchor systems with wedges that grip the bundle of cables simultaneously. Let us see the application of strand jacks when moving a bridge construction element. The strands used in the heavy lifting strand jack applications have standardized diameters of 15.7 or 18 millimeters. It is good to understand how a strand jack actually works. Let us look at the main parts and then watch an animation which will show you the normally invisible movements inside the strand jack. As you can see in the image, strands are guided through the jack with the help of strand guides, which help to keep the strands at a set distance from each other to avoid tangling. Mini jacks on the top and bottom of the jack control the tightening and releasing of the wedges and anchors around the strands. The main lifting jack creates the movement along the strands with the counterbalance valve controlling the oil flow. The chair then is where the strand jack is secured to the construction element. Here is the animation of how the elements of a strand jack are designed to work together to simultaneously pull the strands through the jack. Strand jack systems are, as a general rule, supplied in sets consisting of one set of 4 strand jacks, 4 power packs, 4 fixed anchors, 1 smart cylinder control system, 4 data cables, and 4 hydraulic hose sets. Enerpac offers, apart from the strand jack contents, a number of accessories which are valuable to most of the strand jack customers, such as power packs, strand guides, recoilers, dispensers, wedges, and of course the heavy lifting strands themselves. Next on our list of bridge construction solutions we find the Enerlauncher system. The Enerlauncher is a tandem launching system with 2 units. Each unit consists of a lifting section on a slide plate with push and pull cylinders with a maximum capacity of 1,100 metric ton per cylinder, and a push and pull section for advancing and retracting the lift section. Here the max capacity is 225 metric ton per cylinder. Here is a schematic representation of how the Enerlauncher will move the bridge construction element. As mentioned, the Enerlauncher is a tandem system, so a pair of units. The total lifting capacity is 2,200 metric tons and the pushing force of the system is 900 metric tons. In this overview we try to capture the Enerlauncher system for an extreme angled downward bridge displacement. The system needs to contain a pushing system, a braking system with steel bars and hollow cylinders, as we have seen earlier when discussing the spindle bar system, strand jacks for retaining and as parking brake, a top yoke for increasing the friction force on the Enerlauncher, and in this case also the nose recovery cylinder system and lateral guides, as well as side plates. Customers are looking for controlled movements of their bridge construction elements. The Enerlauncher offers equalized and monitored hydraulic movements to allow control over the bridge sections during launching, and integrated PLC control over 2 or more Enerlauncher systems working simultaneously to allow steering of the bridge. Depending on slope, shape and movement, the bridge construction may need auxiliary systems such as nose recovery systems, monitoring systems, braking, parking brake and emergency braking, and side guidance and leveling systems. Let's have a closer look at these auxiliary systems. Nose recovery systems are used to compensate deflection or the bending downwards of the bridge element when being moved to the next support to cover the span between the piers. Deflection can be calculated and is specified in the bridge construction file. Lifting capacity and required plunger stroke can then be deduced from these data in the file. Looking closer at the nose recovery system, or nose lifting unit as it is sometimes called, we can say that there are 2 hydraulic solutions. In the majority of nose recovery systems we will find a simple system with high pressure hydraulic cylinders. The cylinders are equipped with guides or bearings to overcome side load as a result of radial forces. An electric pump will operate the cylinders, which generally have lifting capacities from 50 to 75 metric tons. A different nose recovery system makes use of a tower system and a movable hydraulic multi-point synchronous lifting system. Characteristics of these tower systems are that cables at the bridge side of the tower are fixed with anchor plates. The cables pull the nose up with high tonnage cylinders, CLL or CLRG, and the system is operated by a PLC controlled pump, as in the EVO system. The size and weight of any bridge and the bridge construction elements can suffer structural problems if movements are not controlled. Structural problems means, for example, high forces, overload, stress, and too high launching speeds. Therefore, monitoring of the following elements is necessary: bridge deflection or bending, the angle of the piers or pillars, the load of the lifting points, and the launching speed. To illustrate structural damage, please watch this extreme example of the influence of wind on the Tacoma Bridge in the US. In a bridge launching operation, the deflection and the angle of the piers or pillars are measured using inclinometers to measure inclination and accelerometers to measure the acceleration or speed of a bridge construction element. Specialized agencies are available to carry out the monitoring of the bridge construction for the construction companies. They will connect their equipment to the system controlling the hydraulic movements. Think of EVO and Enerlauncher. A slope of more than 2 degrees will indicate that a braking system must be put into place for the launching operation. These braking systems are put into place to guide the forward movement, to control sideway movement, to lower the moving speed, and to stop and lock the bridge in case of an emergency. Any bridge with a curved design will need a guidance system on both sides of the bridge to control the movement of the deck. Controlled hydraulics are also applied in these guidance systems. Products and systems for bridge launching can be found in the Enerpac catalog and in the Integrated Solutions brochure. If you want to know more about the Enerpac synchronous hoisting and positioning systems, please check out the Enerpac.com website under Products, Integrated Solutions Heavy Lifting, Synchronous Hoist Systems. If you want to know more about incremental step-by-step lifting using the BLS series stage lifting cylinders, please check out the Enerpac.com website under Products, Cylinders Lifting Products, under Products, Cylinders Lifting Products and Systems, Hydraulic Lifting Systems, BLS series climbing jacks. Information on high tonnage construction cylinders designed for heavy lifting can be found on the Enerpac.com website under Products, Cylinders Lifting Products and Systems, High Tonnage Construction Cylinders. Information on the EVO series can be found on Enerpac.com following Products, Integrated Solutions Heavy Lifting, Synchronous Lifting Systems. Information on strand jacks is also available on Enerpac.com under the tab Products, Integrated Solutions Heavy Lifting, Strand Jacks. Multi-point controlled lifting with the split flow electric pumps is documented on Enerpac.com under Products, Integrated Solutions Heavy Lifting, SFP Series 700 bar split flow hydraulic pumps. Enerpac has put together technical books with detailed information on the EVO series and on the sink hoist and autonomous sink hoist systems, as well as the paper version of this bridge launching training. These books are intended to increase knowledge and understanding, explain the system and capabilities, and contain examples of applications.